This is Statistics 243 at Berkeley for Monday, November 10th. All right. So I left off last time, and we were talking about the world's worst random number generator. You guys travel in the back? So we had the world's worst random number generator, which had A equals 7 and M equals 13. And it was one of these generators where we... Can folks pipe down, please? Thanks. It was one of these generators where we multiplied the previous U value times A, and then we take the remainder when we divide by M. And so I just had walked through that if we used those two values to sort of control the generator, then we end up getting these as the values of U. We start out with 2 and then 1, and then eventually after we get to 4, it ends up looping back around and giving us 2. So there are only going to be 13 or so values in here. So if we actually wanted to generate the random uniforms from this, well, then we just divide by 13, and that gives me these things I'm calling the deviates. And we can see what those values are. One of the things I wanted to mention here in the context of this simple example is we could have a very, very long period, but we might not be able to, on the computer, represent uniquely that many different numbers. Okay, so just because we have a long period doesn't mean that you're going to see that many unique values in the cycle of the random numbers that are generated. So an example here would be, let's pretend we're operating again on a computer that has very limited precision. Suppose it's a computer that operates in base 10, but the best it can do is give us 1 digit of precision, so 0.1 up through 0.1 up through 1.0. So now if I have an algorithm that generates these random numbers, but the best I can do is store numbers that look like this, well then I can think of rounding these guys to get their 1 digit representation. And the period of this is still going to be the same as the period of this. It's still going to be the 13 values. But there are some repeats in here. Like 0.8 gets repeated twice because there are 2 values in here that round to 0.8. Okay, so it doesn't mean, the period doesn't mean we're going to have that many unique values. It just means that we're going to have that long a period until we get back around such that we then start repeating the same subsequences again as we come back around. And that will come up in the actual generator that gets used in R, so I'll comment briefly on that in a minute. Okay, any questions from last time before I talk about a more realistic generator? Okay, so the next sort of somewhat better generator, rather better, but still not as good as the default ones, is this generator here, which takes A to be 171 and M to be 30,269 as opposed to these values that we'd seen before. This is another one of these linear congruential samplers, and I have some code here to actually just generate this from this, where we actually write up the code ourselves, and we can just see this. So if we do that, here's that situation. I'm just generating this vector of U's, and then I'm going to divide by M here in the last highlighted line to get them onto a 0 to 1 scale. And I'm going to compare that with actually using whatever R's random number generator is to then generate random uniforms just by default the way that you would do it in R. So that's just using RUnif. And so if I do this, I can now plot I can basically do a plot that just sort of looks over iterations, just over the number of random numbers that are generated. And we can see what it looks like. Maybe I'll zoom in here so that helps a little bit. So what is it that, if we look at this, what is it that we are looking for? What are we hoping this to look like if this truly is generating from random uniforms? Okay, so we want it to be white noise, and what would that mean sort of in practice? Nick? So yeah, so what would it look like if it's uniform? Just sort of going up and down?
Yeah.
Okay. And what else do we know in terms of sort of how it's distributed across here? It should be, you should have roughly the same amount of points that are down here as here, as here, as here, as here, right? Okay. And what about in terms of dependence structure? What do we expect to see? Right? We shouldn't see any dependence from one iteration to the next, so it should just like it look like it's bouncing randomly around. And if we look at this, you know, if we sort of stare at this, we might be a little bit concerned, like, oh, this looks so weird. Like all of these points, there are sort of 4 or 5 points in a row here that are all fairly similar to each other. So, you know, if we sort of stare at this enough, we might think that we see some sort of dependent structure in there, some places where it sort of seems like it's somehow not giving us uniform random variables. And so part of the challenge if you're developing a random number generator is to be able to distinguish between cases where things are independent, but just by chance we see something that looks like structure in here, and cases where it's not actually chance and the structure is actually a result of the random number generator not doing a good job of giving us things that look like they're uniformly distributed. In this case, this is almost surely just chance that some of these have these sort of places where it looks like they're sort of related to each other over the course of a few iterations. And so this is the uniform numbers generated using R's default algorithm. And this is us just doing our implementation of that simple linear congruential sampler. I don't see anything particularly different about the two of those. So it seems like this, at least from this just very quick assessment, it seems like nothing looks terribly bad about this. But if we were really going to propose this as the sort of the core generator that lots of people are going to use, we'd want to do a lot more careful assessment. The other thing I thought I would do here, we could also do right. So there are 2 more plots we could do. In terms of assessing whether things are uniform in terms of that y-axis of that sort of time series plot, we could, of course, just turn this into a histogram and see how the histograms look and if they look like they're uniformly distributed. And the same sort of thing holds that we were talking about up here. Here we were saying, well, maybe this excursion looks a little bit suspect. Well, maybe this looks a little bit suspect that we don't have enough values. Of course, they're only in relatively small bins because there are only 100 values here, right? So there's going to be some chance variation, particularly if you have a small sample, and you'd have to do some probabilistic reasoning to say whether or not the fact that there seem to be very few between 0.5 and 0.6 is just a result of chance, or could be something about the generator. The other thing I just added as I was waiting for class to start was just to plot. To try and get at the dependence from one value to the next, and also this should also get at some aspect of uniformity in higher dimensions. So I just took those 100 values and filled out a 2-column matrix by row. So the first 2, so it's 1, 2, 3, 4, 5, 6, 7, 8. So that should give us some sense of where there seems to be some serial dependence here. And if I oh, right. I didn't actually define that as a matrix. Okay, so if I do that, I can get some sense of, A, whether or not there seems to be any sort of dependence here. And also, the scaling is a little bit awkward. It'd be nice to have this so that this was a square and not a rectangle. So it doesn't look like there's any obvious dependence pattern here. But the other thing to look at if we're doing this, if we're just thinking of this in 2 dimensions, if it's going to be random uniform in 2 dimensions, we want the dots to basically fill out the entire square. And more generally, and I comment on this in the notes, we basically want any subsequence of length k to fill a unit cube in k dimensions. Okay? And so in this, this is obviously just a unit cube in 2 dimensions. And it doesn't look like anything's particularly terrible, but we want to generate more random numbers to really assess that. And what happens with random number generators that people decide are not particularly good, it often happens is they start looking in k-dimensional unit cubes and realizing there's some structure in there that it doesn't seem to be filling out the entire k-dimensional unit cube in a very good fashion. And that's one thing that then leads people to look for better generators. Okay, questions or comments? Yeah, Kelly.
Has that ever been a huge problem anywhere that people have found that they use some random number generator only to find that it actually had patterns? Or is there some algorithm that was originally thought to be good, but then later found to have these problems with it?
Yeah, I mean, there's a whole history here of, I don't know exactly when it started, I haven't sort of looked at the details, but my understanding is over sort of the last 50 years or so with the advent of actual modern computers is that people have generated more and more sophisticated algorithms that perform better and better on these tests of whether or not they're generating actual random uniforms. And there are cases where some of the more naive ones, and I think it's the case that like in some old, if you went back to C in the 1970s, that they would have a generator that didn't perform particularly well. And what sometimes happens, so I think an example of this that I remember from when I was developing these materials is, if you looked, and this might have been not in two-dimensional subsequences, but k-dimensional subsequences, is that all of the random numbers sort of lived in this sort of structured set of lines like this. So there are definitely cases where people have seen that sort of naive or sort of some of the original implementations had some deficiencies. Did you have a comment, Chris?
There was actually a statistician in Texas that won the lottery 3 times, potentially by identifying an error in the random number generator.
Okay. That's a nice story. So yeah. So not just academic in its interest. Okay, so that was a sort of realistic generator, somewhat simple but fairly realistic. Turns out one of the random number generators that you could choose in R is something called Wichmann-Hill, and Wichmann-Hill is basically a combination of 3 of these linear congruential samplers, one of which is the one I just mentioned, which was the 171-3269. So Wichmann-Hill basically combines one sampler with this value for A and this value for M, another one with this for A and this for M, and another one with this for A and this for M. And maybe I'll go back to the notes. So the definition of it is that the U's are, so X is generated with one pair of A and M, Y with the second pair of A and M, and Z with the next one. So we take X divided by its M, Y divided by its M, Z divided by its M, add them together, divide by 1, and get the remainder. So part of the reason I wanted to show you this was just to show that we could actually implement one of the random number generators that's in R, and the other is to highlight the idea of what a seed actually is here. So let me go back to the R code. Okay, so what I'm going to do here is I'm going to set R's random number generator to be this Wichmann-Hill generator by using this RNG-kind function. And then I'm going to set the seed, and I'm going to save that seed for us to come back to it and look at it, to use it in a minute. And then I'm going to generate 10 random uniforms from using R's RUnif function. And now what I'm going to do is I'm going to generate 10 random uniforms using Wichmann-Hill where I actually implement it manually myself. So XYZ is going to contain the X, Y, and Z values. And I'm going to start off the first XYZ triplet by taking the second through fourth values from the saved seed from R's random number generator. So what we'll see is that the seed for the Wichmann-Hill is basically the X, Y, and Z values of the starting position. Okay. So I'm going to start this off with that starting position, the starting position from before I generated the 10 random uniforms. So what I should be doing is, with my manual generation, I should be generating exactly the same random numbers that are generated using Wichmann-Hill, using R's RUnif function. So I'm going to generate the first triplet of XYZs, and then for 2 up through 10, I'm going to generate those corresponding XYZs. And then I'm going to generate the random uniforms from the XYZ triplets by doing what I had in the PDF, which was summing up the each XYZ value divided by its M. I'm doing this in a vectorized fashion in R, and then doing the remainder when dividing by 1. So if I go ahead and do this, what we'll see is that I do indeed generate exactly the same numbers with my manual implementation and with R's uniform implementation. So just a little bit of proof of concept. And then to talk about the seed, so remember from last time we said, okay, we've got this periodic pseudo-random sequence of random numbers. The seed basically tells you where you're starting in that circle of numbers. And if we set the seed to be the same thing, we're always going to get the same sequence of values, so we can replicate what we've done. So now if I look at, let me just look at the whole x, y, z vector. So it looks like this. So this is just the value, the x values, these are the y values, these are the z values. And this should now be the value of the seed at the current moment. And if I know these three values, I can basically pick up and continue along, because I can then use the x value to get the next x value, the y to get the next y, and the z to get the next z by using the a, multiplying by the a and dividing by the m and whatnot. And if we look at what .random.seed is, which is this sort of internal R object holding the information about the seed and actually about the generator, what we'll see is what the 400 means is that specifies the type of random number generator. So the 400 is actually just a code for the Witchman-Hill generator. And then these are the x, the y, and the z values for the sort of current position in the cycle of random numbers. And these are exactly the same as what I got by starting my generator using the values from R's random.seed 10 values ago, generating the 10 random numbers, and then the value of the seed is wherever I happen to have gotten to in the x, y, z space. And I could, well, never mind. Okay, so I guess the other comment here is when we do set a seed, we're not actually setting all of those three numbers. And for other generators, it's going to be more or less than three numbers. It's not always going to be three numbers that serve as the seed. So the idea of what the set.seed function does is basically there's some algorithm that takes the number that you give in, which is a single value for the seed, and basically somehow or another comes up with, in the case of the Witchman-Hill, the three values, the x, y, z, and in the case of other generators, all of the numbers that are needed to serve as the seed for that particular generator. So sort of the length of the seed varies with whatever the generator is. And I haven't actually looked into exactly how that's done. But the hope, and this is not something that's clear that you can rely on, the hope is that if I've got my random number generator, and I said set.seed of 0, suppose that started me here, and then I said set.seed of 1, hopefully set.seed of 1 would not put me in a place that was really close to set.seed of 0. Hopefully set.seed of 1 would give me a place that was rather dispersed away from where set.seed of 0 put me. Set.seed of 2 would hopefully also put me in a place that was sort of far away from the other ones, and so on and so forth. But as far as I can tell, it's a little bit hard to tell from the documentation. Doesn't seem to really much guarantee that if I choose different seeds, I'm necessarily going to be far away, although there's some sort of vague language that says you should, that you may, or you should, I don't know how exactly it's phrased, get sort of dispersed starting values here. All right, so any questions or comments? All right, let me remind myself where I am here. Okay, so it turns out that the default in R is something that's thought to be somewhat more sophisticated than that Witchman-Hill one, or those congruential generators in general. And what it basically does is, it's called the Mersenne Twister, and it's one of these things that are called generalized feedback shift registers. So what does that mean? So it basically means that we have a long sequence of bits, so a long sequence of zeros and ones. And the way that you determine any given value in the sequence is it's some function of a pair of previous values in the sequence. And exactly how you choose which two then get mapped on to determine the next bit is sort of a detail of the algorithm. So the idea is you get this long sequence of zeros and ones, and then the way that you get a random number from this is you take a subsequence here of a certain number of bits, let's say L bits. So this is going to give us a base 2 number with L different bits. We can then convert that to base 10. And that's basically the way that we get our random numbers. And so here would be in the next sequence of L numbers. So this would be, say, this would give us what in the previous notation we were calling UK, and then this would give us the next one. This is UK, plus 1, and so on and so forth, and we just sort of keep marching forward. So there's been a lot of testing of this generator. People seem to think that on these empirical tests for whether it passes tests about being a good random uniform generator, that it does perform well, and it turns out to, do I say this somewhere? I must say this somewhere. Oh, I say this down here. Turns out the periodicity of this generator is 2 to the 19,937, which is about 10 to the 6,000. So 10 to the 6,000 is a pretty darn big number. So the period is, that it takes a long time to get back around to the starting place. And then the other thing about the seed is that the seed for the Mersenne Twister is a set of 624 different integers. So the Witchman Hill, we had 3 values serving as the seed. For the Mersenne Twister, it's rather more complicated. We have this whole set of a very large number of integers that's serving as the seed. And so if you did just look at this, we'll see indeed when we look at this that there are 625 values in here. So remember, the first number in this in the vector, in the seed vector, is going to indicate what the generator is. So 403 codes for the Mersenne Twister, and then this is this set of integers that I just indicated as serving as the seed. Okay, so let me say a brief word about replicability. So one rule of thumb is if you're going to use random numbers, if you're going to do a simulation study or anything where we're using random numbers, it's a good idea to set the seed at the very start of your code, because otherwise what will happen is you'll run some code and you'll get some result, and maybe it'll look a little weird, and you'll be like, huh, I wonder what's going on there, and you'll want to go back to the beginning and basically rerun your code to be able to see what's going on. But because you don't know what the seed was, you won't actually be able to run it exactly the same way as you already ran it. So you won't have any repeatability from redoing the operations 2 times. So it's always a good idea to set the seed at the very beginning, and then if you need to generate the exact same results, you can do so by resetting the seed to the same value. So just as a simple example of that, if I set the seed to be 0 and generate 10 random numbers, okay, I get those, oops. If I set the seed to be 0, generate 10 random numbers, I get those 10 random numbers. If I now reset the seed to be 0 again and generate another 10 random numbers, you'll see that I've done something, I've just gotten exactly the same numbers back again. So any functions that I apply to these random numbers, obviously I would get back identical results as well in both of these 2 runnings of my code. And the other thing we can do is we can actually save the seed and then reuse it potentially. So usually you would just want to get repeatability by just using the same seed, but it is possible to do the following, which is, suppose I set the seed to be 0, I generate 5 random numbers. I'm going to save the value of that .random.seed in something I'm calling saved seed. And now suppose I do some other operation that involves using random numbers. In this case, I'm going to use the sample function and do some random sampling. I can generate the same, I generated 5 random normals. I can generate the next 5 random normals by basically going back to whatever the seed would have been after the first 5, resetting it, and then generating my 5 random numbers. So now I'm going to set that random.seed to be the saved seed from just a couple lines above and generate another 5 random numbers. And if I do this, what we'll see is, okay, the first 5 began with the 1.26, the next 5 began with a minus 1.539, and if I go up a little ways to when I generated 10 all at once, here's the 1.26 again, and here's the minus 1.539 again. So it's basically just breaking up those 10 that I generated into 2 chunks of 5 and generating 5 at once, doing a bunch of other stuff and generating the next 5, but I basically have full control. Yeah?
So when we create a seed or set up a seed, do we somehow create a new environmental variable or something? Or just like underlying?
What do you mean by a new environment? I mean, this is all in the global environment.
Okay, so it's a global environment. We somehow create a new variable.
Well,
that we can use that later.
What do you mean a new variable?
I would set up C to 0. So would that mean I would create a new global variable that we can use for different functions?
Well, it's not that we're creating a new variable. It's that when we set the seed, it's basically setting the value of this sort of internal variable. Does that help?
Yeah.
Okay. All right, other questions? Okay, so let me just say a few brief words about generating random numbers in parallel. So let's go back to what I was talking about in terms of the seed over there. Now suppose that what I'm doing is I'm doing some sort of simulation study, but I want to do it faster, so I decide to start up a whole bunch of different processes to do my simulations. Okay. So let's just take a silly example. Suppose I'm trying to understand the property of the means of random normal or random variables. Okay, and suppose my simulation study is for I from 1 to m. Each one of these, I want to get the mean of a random normal vector of IOD random normals, where there are, say, very, very many of these random normals. Okay, so a billion in this case. So for each of these, I'm going to do a mean of R norm of 1e to the 9. But I say, well, maybe this will take a while to generate all these, so I'm going to split this up, and I'm going to do this set of m tasks in parallel using, say, for each, which we saw in the unit of parallel processing. So if I'm going to do this, what could go wrong in terms of the fact that I'm using random numbers? Okay, so how would I get exactly the same random numbers? Okay. Yeah, if somehow or another I wasn't thinking about this and I wrote my code such that I was calling some function, each of the, let's suppose that I've encoded this mean of random norm in a function, and in that function I wasn't thinking about it and I just say set.seed of 0. Right? Well, that's a little bit silly, but it's the sort of thing that could happen if you're just not thinking about it. Well, every set of these 1 million random numbers is going to be the same set of 1 million, so you're just going to get the same value repeated over and over again. So obviously we don't want to do that. So what if I'm now thinking about, well, how do I go about setting the seed to ensure that this performs the way that I want it to perform?
So a couple of seeds that will go and then send it to the parallel, each kind of seed.
Send what to the parallel?
Different seeds.
Okay, so I could basically number these tasks from 1 to m, and for each one I could say, in this one I could say set.seed of 1, and here I could say set.seed of 2, and so on and so forth, right? So that what that means is, okay, wherever 1 puts me, I'm going to get those numbers, and wherever 2 puts me, I'm going to get those numbers, and wherever 3 puts me, I'm going to get those numbers, right? So what could go wrong with that?
Maybe that you set seed in 1 and you have this, and then set it to slot 0.
Okay, so yeah, so that's sort of what I was saying before, is there's not necessarily any guarantee, particularly if you're generating a lot of random numbers, that we'd actually have these being distinct blocks, right? So I could get unlucky in some fashion, and maybe my 1 seed puts me here, and my 2 seed puts me just a little bit further along. So what's bad about that?
A lot of
Nick?
having a lot of overlapping of the data.
Yeah, so statistically what would overlap how would we describe what the overlap is causing in the case of these results? Right, there's correlation or dependence between, potentially correlation or dependence between some of these, because let's say in this case, these two processes are basically computing fairly correlated means because they're using a lot of the same random numbers to generate those means. So we're sort of at the mercy of whatever the seed generating process is to hope that we're not going to get this kind of overlap and it's not going to affect the results we get. Okay, so that's basically the problem. It's probably in reality not a huge problem. the periodicity of this sequence, especially for the Mersenne Twister, is very long, and there's some vague indication that that if you set the seed, it probably gives you positions in the cycle that are fairly far apart. But it's usually good to be safe about this. And so there is actually a fairly easy way to do this. So one thing you could do is you could just generate all your random numbers on one process and then basically divide them up yourself in a way that makes sure there's no overlap between them. So that would really only work if the random number generation were a small part of the computation, because otherwise you lose the benefit of actually doing the computation in parallel. But it is one possibility. But there is also a way to do this where this is sort of all accounted for, and in particular there's this R-LookU algorithm, which is encoded, which has been coded up in terms of an R package called R-LookU. So sorry, the algorithm is called LookU after the French mathematician who came up with it, and this is the R package. And basically what it does, as I've sort of indicated here, is it sets up, doesn't use the Mersenne Twister, it sets up a different generator where the period is 2 to the 191, and it divides it up into disjoint subsequences of length, whatever I said there, 2 to the 127. So there are a whole bunch of these different subsequences, whatever 2 to the 191 minus 2 to the 127 is, are divided by. There's a whole bunch of these different subsequences, and if you use this package, you can basically ensure that each of the processes is going to get a different chunk that is distinct from the other processes. So there's a whole bunch of detail in here that I don't think is worth going into of how you would actually use it, and just the syntax of doing it. Basically, the core function that you would use with for each is this cluster set RNG stream, and by default that's going to set it to use this LookU algorithm. And then you can go ahead and use some of the various parallel excuse me, some of the various parallel functionality that R provides. So yeah, I don't think I want to go through any of the syntax here. There are a lot of different examples if you were actually doing this in practice. Okay, so let's move on to other methods of generating random numbers from particular distributions. So we've spent a bunch of time on what are the random number generators that you could use to generate things that look like they're random uniform numbers. So then the challenge is, the next challenge is going to be, well, in a lot of cases we need to generate from some other distribution that's not a uniform distribution. In a lot of cases there are already well-developed algorithms to do that for lots of the well-known distributions that are used in statistics. And those are already coded up in R norm and R gamma and R chi-square and R beta and all of the other R blah functions in R. An example of this is there's a standard algorithm for generating a random normal. If you take 2 random uniforms, there's a standard algorithm for getting a single random normal out of 2 random uniforms. So since these are all sort of well known, I'm not going to discuss those. We discussed last time in the linear algebra unit how you would generate from a multivariate random normal with a given covariance matrix using the Cholesky decomposition, so that's there. Most of you have probably heard of the inverse. Well, okay, so now let's move on to what if you have some distribution where you know what the CDF of the distribution is, or the PDF of the distribution. How would you go ahead and generate a random number from that distribution? So in many cases there are known algorithms to do that. If you can invert the CDF F and get F inverse, then you can use the inverse CDF method. You could generate from a random uniform and basically pass it through the inverse function to get something from the distribution of interest. So that's well known, and many of you or most of you will have seen that. So the ideas that I'm going to talk about for the remainder of today and maybe a little bit into Wednesday are some algorithms for generating from distributions where we can't use inverse CDF and we don't have some known algorithm for generating from the distribution. So the first of these is a standard algorithm called rejection sampling. So here's the idea of rejection sampling. So suppose we have some PDF density function f, and suppose it has some funky shape like that. For the moment, I'm going to assume that this goes to 0 at some finite value, just for the simplicity of drawing some of the pictures. So the idea is, if you give me an x, I can evaluate f of x. But I don't have any known algorithm to give me random numbers that are generated from this distribution. So the standard rejection sampling algorithm is, if I can come up with some other distribution, which I call G here, and if that distribution, when I multiply it by a value C, is always at least as big as f of x, then I can use this to generate from G and do a correction, basically, to be able to generate from f. So the idea is I need some G that when I scale it up by C is always going to be above this distribution. So suppose I can come up with this magic G, and G looks something like this. Or G, when I scale it by C, looks something like this. So this is C times G of x. I know that this is not the original density G of x because f should integrate to 1, so G can't integrate to 1. Or this particular curve doesn't integrate to 1 because it's obviously above f. Okay, so if I know this, if I have G and if I can generate from G relatively easily, then the idea is that I'm going to generate from G. So I'm going to generate some x from G. So suppose I generate this x from the G. And then I'm going to generate a uniform random number between 0 and 1. And then if U is less than the ratio of f to C times G of x, I'm going to accept x and use it, and otherwise I'm not. And what basically that corresponds to is I'm basically saying the generating the random uniform in that decision in step 3 is basically saying, am I in this part of this line or am I in this part of this line? So it's basically like I'm generating a whole bunch of numbers basically under this curve. They correspond to numbers in a bivariate space, a sort of augmented space that's x and u. So I can think now I have this sort of bivariate space of x and u. I'm basically generating uniformly in this area that's under the C times G area here. And then I'm basically chopping out everything that is above the curve, and that's going to leave me with points that are basically generated uniformly in 2 dimensions from this sort of funny shaped thing here that has the curvy shape that comes from f augmented by the axis here. And basically the reason this works is that I can basically write the marginal distribution, if I consider u and x jointly, right? I'm generating from a bivariate distribution u and x together. But if I consider the marginal distribution of x marginalizing over u, you can basically work it out really easily. That does end up being this generating from the original distribution f that I'm interested in. And sort of the geometric interpretation is nice, that I'm sort of generating in this bigger shape, and then I'm sort of chopping out the pieces that correspond to parts of the shape that are sort of outside of the shape of f. Okay, so what are the challenges here? Well, the challenge here is we need to find a G that works for doing this and that is easy to generate from. And in some cases that might be fairly straightforward. In other cases that might be kind of hard. And the other thing is we don't want C. We don't want the amount of area in between the G and in between f and C times G to be too big. Because every time we get a point that's in this area, we're basically wasting computation because we have to throw that value out and we can't keep it as part of our sample. So basically, it turns, if you just do the basic integration, the value 1 over C turns out to be the acceptance ratio, the proportion of values that you accept. And so you can imagine you wouldn't want some G that looks like this, or some C times G that looks like this, because most of the values that I generate from that are going to be thrown away, and I'm going to have to be doing a lot of computation per value of x where I actually accept that value. Okay, so questions about that? Yeah, Julie. No?
Oh,
Yeah.
well, I read a little ahead and said that they do piecewise exponentials. Is there a reason exponentials are used and not polynomials?
Yeah, I'll talk a little bit about that in a few minutes. Let's see. So, other questions? All right, so let me show you a little example here. So the example is, yeah.
In the integral relation over C, that only holds true if g of x has the same shape as f of x, which the most recent example is not correct.
Well, G is always going to be a density. This was G if I scale it up by C in some fashion to make sure it's over F everywhere.
Right, the ratio of rejected points to accepted points being 1 over C, the integrals.
Uh-huh.
The integral for g of x would have to be equal to the integral of f of x.
Right, but they're densities.
Right, so g of x and f of x have to be the same functional shape. For the C would just be pull down the integrals. Then it wasn't at the same area under the curve.
Right, but they're densities. So the integral under F is 1 and the integral under G is 1.
Okay.
So just, okay, that's fine. Yeah, no, I'm not, it's fine. I don't want to, I'm just, yeah. Okay, so that was all the parallel random number generation stuff. Okay, so here the example is, and this is sort of a well-known example in statistics. Suppose we wanted to generate from a random normal distribution, but we wanted to generate from a truncated version of this distribution, where we want to generate from the random normal constrained to be bigger than some cutoff, which I'll call, do I have a name? Tau, which I call tau. So I want to basically generate from the tail of the random normal. So basically, if this is a truncated distribution, then basically we just have to scale this thing up so that it integrates to 1, so it's a legitimate density. So what's the most naive way that I could generate from this truncated normal distribution?
Check if the value is greater than tau.
Yeah, so I just generate from this random normal, and the only ones I keep are the ones that are bigger than tau. Okay. If I'm really far out in the tail here, what's the problem with that?
Very few.
Right, I'm only getting right. If this is the 0.999 quantile of the distribution, I'm only going to accept 1 in every 1,000 of the values. So it's going to take a long time to generate these numbers. In fact, what I'm just saying here is actually a rejection. Is already a rejection sampler because I'm using this as my g of x distribution, and then I'm basically only accepting the values that fall in here, and anything that falls in here I'm rejecting. So there's sort of a way of looking at it that's just what we've already seen. Well, okay, so what could I do in this case if I wanted to be smarter about this? Well, I would try and come up with some g function that basically only lives out here, and that is then when multiplied by c is always going to be above the tail of the normal distribution. So one way to do this is, I know it's easy to generate from an exponential distribution. I can do that by inverse CDF, for example. And I also know that the tail of an exponential distribution is going to be much, much fatter than the tail of a normal distribution, because the normal distribution is decaying as e to the minus x squared, and the exponential distribution is decaying as e to the minus x. Okay. So the idea is to set up an exponential distribution, and now if we sort of blow this up, what it's going to look like is basically, here's my normal distribution that's decaying really fast. And basically, I'm going to find the right exponential distribution such that it sort of looks like this. And it's going to touch at some point here. And as we get on the tail, this is basically going to be many, many orders of this c times g is going to be many, many orders of magnitude bigger than f. Okay. But since I'm generating from G, I'm not actually going to get very many values generated out here. So even though if I do get a value out here, it's almost always going to be rejected, there aren't going to be many values generated out there to start with, because even though the exponential tail is decaying more slowly than the normal tail, the tail is still decaying quite quickly. It's still decaying exponentially fast. So that's the idea in this case, is to not generate from all of this bulk of the distribution, to only generate values bigger than tau. So the example here, and I won't go into all the details of exactly the computations, it basically involves playing around with thinking about standardizing a normal distribution, so subtracting off the mean, dividing by the standard deviation, and stuff like that. So I'm going to try and generate from a normal distribution with mean 1, standard deviation 2, for values. I'm going to try and generate with my tau being bigger than 4. So here I'm just doing some setup. Here's the original sampler where I just generate from the random normal and only include the values that are accepted, that are bigger than tau. Okay, so if I do that, that's the random sample there. And this is the acceptance ratio. This is only 6.8%, about 640 out of the 10,000 are accepted from this sampler. So it's fairly inefficient. So now I'm going to set up my exponential distribution. This involves the standardization I was talking about. I can actually calculate the value of C in closed form for these easy distributions, which are just normal and exponential. And so I can generate from Y, which is generating from the exponential that I've set up from this parent G distribution. I can generate my U's, which are the auxiliary variables that we've talked about. And then I can only accept the ones where U is less than that ratio of F over C times G of X. So this is just the encoding of that in the actual example. And then I have to sort of reverse standardize because I've done some standardization because of the normal distribution. So those are just details. But I get this set of values SAMPS2, which is my second set of samples from the tail of this normal distribution. And if I look at the length of the number of accepted ones divided by the 2,000 that I generated, what I'll see is that in this case I actually accept 91% of the samples, which is much better than the 6%. And in this case, because things work out in closed form quite nicely, I can actually find out that the theoretical acceptance ratio is this 1 over C, and it's 91%. So it looks like in practice we're getting basically that. So the nice thing about this is just to sort of see the picture of what's going on. So this is meant to show in black the rejected samples and in red the accepted samples, and it's supposed to be basically showing me a sort of empirical version of what I was showing here, which is basically the C times G touches F at one point, and that's basically at this point here where everything is being accepted. So for values around 2, it looks like everything's accepted. For values less than that, there are a few points that are rejected corresponding to points that fall into this little area here. And then as we get out in the tail, all of these points are being rejected. So basically out here, everything's getting rejected, but like I said before, we don't end up proposing very many values out there because we're out in the tail of the G distribution as well. So that's out here where basically this is many orders of magnitude larger than this, so everything is rejected. Okay. But it sort of shows pictorially what's going on. And then I can go ahead and just plot, what do I have here? Okay, so this is basically just me on the computer replicating what I had here, which is the red curve is the true F, and the black curve is the C times G. It sort of touches somewhere in here, it's a little bit above, and then it's, in absolute terms, it's a little bit above here. In relative terms, it's a huge amount above out in this tail. And if you did look out, you could sort of then, this is just going to plot. So this was going from about 2 up to 10, or sorry, about 1.5 up to 5 or so. I'm going to plot values from 5 up out to 10 here, just to sort of see what's going on in the tail. And so this is basically what's going on in the tail to illustrate this idea that the black curve is much higher than the red curve once you get far enough out in the tail. So here his value is only bigger than 5. Okay, so any questions or comments? Yeah.
I do have a question. So, computational efficiency aside, is there really any reason you want to do that exponential thing as opposed to saying if sample is greater than tau? Just kind of thinking in lines with best practices, they both seem to take the same amount of time, and that the code was only a few lines of the rejection and was a lot more readily apparent what was going on than all of the.
Yeah, I totally agree with you. If this is sort of illustration in a case where if I were generating if I were trying to generate billions of values from this tail, it might matter. If I'm generating 100 or 1,000 or probably even 1,000,000, the amount of time it takes to do the rejection, to just generate from the normal and reject is probably going to far out, and the benefit of just being clear in your code is probably going to far outweigh the computational benefit.
Because you did 10,000 and it took, you know,
Yeah, right.
no
It was like that. Yeah. So this is not a realistic example if I'm just generating 10,000. But the idea is if I really were generating many, many, many of these, then I might need to do something like this. So. Okay. So I'll say a few more words about a couple other kinds of sampling next time, and then we'll start in on the optimization unit. And I will see all of you in a few minutes or in an hour or so. It's in section.
So you practice G's only.
Huh?
You practice G's only having the tails, right?